Okay, great. Sorry, technology hates me. Okay, so this first function, y equals 2 to the x, exponential function. Let's talk about some of the key points, because the main way that we're going to be graphing is by using transformations. So if you don't have a general idea of what points are going to be included in this graph, then your graphs with transformations are going to be pretty terrible. So a couple of important points. This one right here. Every exponential function that has not been shifted left or right or shifted up and down will go through the point 0, 1. Somebody tell me why. Because anything to the 0 power is 1. True? Okay, so it doesn't matter what I make the base, so I can turn these on, these other two, and they all go through that same point. Okay? All right. Then y equals 2 to the x is always going to go through the point 1, 2, maybe. Right there. Yep, right there. Okay? It's always going to go through the point 1, 2. How come? So 2 to the first power is 2, right? So when I plug in a 1, I get out a 2. What does this function go through? 3 to the x. It will go through the point 1, 3. Ish. It hates me. It's fine. Yeah? What will this one go through? One half ish. It really does. Okay? Okay. What else? There's one other point I want you to be able to use. So 0, 1, always. 1, whatever the base is. And then there's one more point to help you draw that graph that I want you to use. And it's when you plug in a negative 1. Do you remember what happens with negative exponents?
It cuts in. It shortens it.
Negative 1 has a y coordinate of 0.5. Why? When you have a negative exponent, you take the reciprocal of the base. So right now, the base is a 2. If I raise it to a negative first power, it takes that 2 and flips it and puts the 1 on top and the 2 on bottom. Yeah? So those are going to be we'll kind of refer to them as like the anchor points or the starting points for your parent function. Then we can move it all over the place. Okay? So let's check. Do these go through that same process? So 3 to the x has a point at 0, 1. 3 to the x has a point at 1, 3. Oh, I found it first try. Did you see that? I'm so impressed with myself. And then 3 to the x has a point at what? What would this be? Negative 1, 1/3. So 0.333-ish. It's all very ish today. There it is. Look. Negative 1 and then 0.333. Okay. What will it be for this one? 0, 1. 1/2. 1/2, right? Maybe somewhere. Yep, there it is. And negative 1. What happens to 1/2 when we flip it? 2. So what's the difference between these two graphs?
They are reflected.
They're reflected over the y-axis. What else? One of them is called exponential growth. What's the other one called? Exponential, I heard it. Say it louder. Decay. Such a sad word, right? You're growing and now all of a sudden you're decaying. Sorry about it. Okay. Okay. All right. Then we have this little friend. Yay. What is that? What is E? Raise your hand if you learned about E last year.
Isn't it natural?
Yeah, E is what we call the natural base. Okay? It's like 2.718, yada, 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 yada. Okay? E is what we call the natural base. I have a question. Are we still going to have the same 3 anchor points here? Do we have a point at 0, 1? Yeah. Where is the output going to be when I plug in 1? It's going to be the base. What's the base? E. So at 1, it's going to give us 2.718-ish. It really hates me. Oh, nailed it. So that's E. So then what's going to happen at -1? 1 over E. So 1 divided by 2.718, less than a half. Somewhere. Does that make sense? So the same values still apply. I'm not changing anything. I'm just using a very unique number as the base. Okay. When do we use E? When does E appear?
I forget.
You forget? It's in nature.
Oh yeah.
Things that happen in nature grow with a base, grow exponentially with base E, not necessarily with any other base.
Yeah, it's weird.
So like population growth, plant growth, and then also decay if it's 1 over E.
Isn't it like the swirl thing of like the perfection of the swirl thing? That type of
I don't
You
know.
know what I'm talking
Yeah.
about, right? Because it seems to have some.
Yeah, I know we use phi with that, like the golden ratio, but I don't know that I've ever used E with it. Anyway, okay, so now we're going to focus for just any questions about exponential functions, just in general, just growth. With any of those 4 functions that I just showed you, 2 to the x, 3 to the x, 1/2 to the x, and e to the x, with any of those, could you plug in any number and evaluate it? Does that seem pretty easy? Okay, good. Okay, let's look at transformations. Transformations have not changed. You just haven't practiced them with these type of functions in a while. So what is this one going to do? When I turn this one on, what's it going to do? With a +1, what's it going to do? So it went from 0, 1 to what? 0, 2. It shifted everything up 1.
When it's before, it's y.
It actually doesn't matter if it's before or after. What matters is if it's with the x or not with the x. Yeah? So is this particular 1 right here, is it with the x? No. Does it matter if it's over here? Same function, right? So a +1 that's not in the exponent with the x is still going to shift the function up 1 unit. So every anchor point that we had on our red graph, so this point and this point, that's there somewhere, these points are all going to get shifted up exactly 1 unit. Yeah? Same thing over here. You went from 1 to 1/2, or sorry, -1 to 1/2. Now it's going to go up an entire unit to here. What do you notice happens on this side of the graph? On the left side of the graph, what seems to be happening?
The asymptote moves up 1.
Aren't we done with asymptotes yet?
No.
No, look at that.
Funny.
Those look like really flat horizontal lines. They're not. I mean, they are, but they're not. They look like they are, okay? But they're actually approaching an asymptote. Exponential functions only have 1 horizontal asymptote, okay? Why is there a horizontal asymptote on the x-axis? So let's just go back to just the red graph for a second. Why is there a horizontal asymptote right there? Let's think about this for a second. This output right here, when I plug in 1, gives me a 2. Then I get a 1. Then I get what? 1/2. Then I get a 4th. Then I get an 8th. Then I get a 16th. What are those numbers getting really close to? But are they ever going to reach 0? No. Okay. So if you take a distance from the x-axis and you just keep cutting it in half, do you ever actually get to the x-axis? No, because cutting it in half is never going to make it drop below 0. It's never going to make it negative. So these graphs never cross the x-axis. So when it asks you in your homework for the asymptote, if it hasn't been shifted up or down, the asymptote is always at what? At y equals 0. Say that. When I ask you for the equation of an asymptote, I want the actual equation. I want the y equals with it. If it's a vertical asymptote, it would be x equals whatever that number is. Okay, so make sure you do that. Okay, so back to transformations. This one shifts it up 1. What is this one going to do? Negative 2 to the x. What's it going to do to the graph? Is it making the x's negative or the whole function negative? The whole function. So it's going to flip it upside down. Ready, set, go. Okay. But if I put the negative in here instead, what does it do? It flipped it over the y-axis. So you got to pay attention to that negative and where we put it, okay? So a negative in the front, whoa, flips it over the x-axis because it makes the whole function negative or the y values negative. A negative in the exponent with the x is going to just make the x's negative, so it flips every x from being positive over to being negative. Good? Okay, what does this do? When 2 is raised to the x minus 1.
Then it moves over the x-axis plus 1.
Good. Opposite of what we see, right? Does that look like it moved over 1? It kind of looks like it moved down, huh? If you're not careful. So look right here. There's our point at 0, 1. Where's this now? At 1, 1. Right? And then we had a point at 1, 2. Where is it now? 2, 2. It just shifted it over 1 unit. Good? Transformations are not changing. Everybody okay with that? Even if it's e to the x, even if it's this weird function, the transformations are still going to be there. Okay, so I could do e to the x. What transformation do you want to try? Tell me a transformation. Should I shift it? Should I reflect it?
Times it by 6.
Times it by 2, I heard first. What is that going to do?
So it's gonna compress it vertically. Wait, no, stretch it vertically. Yeah, stretch it vertically.
Does that look like the purple graph got grabbed and pulled up? You see that? It's doubling. It's always, do you see it? Even in this little tiny space, can you guys see this right here? Even in this little space right here, do you see how the green graph is twice as far away from the x-axis as the purple graph? And then like right here, do you see how the green graph is twice as far away from the graph or from the axis as the purple graph? Yeah, right here. Green is twice as far away as the purple one. Yeah? Okay. What else? What's another transformation we could do?
Multiply it by 6 and then add 4.
Where'd it go? Yeah, do you see why we can't see it yet? Where would the asymptote be? Where is the asymptote of the purple one right now? 0. And where did I move this graph? Up how far? 4. So where's the asymptote now? At 4. You see it? What else did we do besides shift it up 4? Now all the points are 6 times as far away from that asymptote. So our point that was at 0, 1, yeah, that point is 1 unit away from the asymptote. Look at the green one. It is now, here's the asymptote at 4. It is now 6 units away from the asymptote up at 10. Good? What happens if I put a negative in front of this? Oops. So what all has happened to that green graph?
It's gone through a lot. Vertical stretch.
We stretched it out, we flipped it over and moved it up 4. So this plus 4 is always going to tell you where the asymptote is. Yeah? Okay. All right, any questions about that stuff? About graphing? We're okay? Really quick, let's talk domain and range. What is the domain of the purple graph? Domain. So x, y's, from the x's, it goes all the way to the left to negative infinity and all the way to the right, positive infinity. What about the range of the purple graph?
It would be parentheses 0 to infinity.
Why parentheses 0?
Because it doesn't go to the point.
Because there's an asymptote. It doesn't ever touch the x-axis. Okay, domain of the green graph. Negative infinity to positive infinity. Range of the green graph.
Negative infinity to 4, and both of them are parentheses.
Negative infinity to 4, both parentheses. Everybody good with that? Yeah? Okay, I only heard like 3 people answering, but some of you are nodding your head, so that helps me a little bit to know if you're getting it. It's great. Okay, so half of your first stuff, or half of your first assignment, your first lesson, whatever, doesn't matter what it's called. Half of today is graphing. The other half of today is financial math. Yay. Money, 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 money. So here we go. Compound interest.
Oh no.
I know, it's a good time.
Do we have to memorize this?
Yes, ma'am.
Oh.
Okay, but look how easy this is when you break it down. Okay, just don't worry about writing it down right now. It's all available for you on Canvas, or you can write it down in a second. Right now, I just want you to listen. This is just how much money you have. Okay, A for amount. So the amount of money in your savings account. Got it? Okay, with respect to T, which is time, because the amount of money in your bank account varies depending on how much time it's been sitting in there collecting interest. Okay? P is for principal. It's how much you put in your bank account in the first place. Okay? It's how much you started with. So when you multiply P by something, you have to multiply it by something a little bit bigger than 1. Otherwise, it's going to be getting smaller, right? If you take the money in your bank account and you keep multiplying it by like 0.75, you're getting less and less and less money. And you're crying. Every day you're crying because your money just keeps going and going and going, right? Imagine every day you take your dollars and you exchange them for 75 cents. And then you take your 75 cents and exchange it for whatever 75% of 75 cents is. Does that sound sad? Yeah, we don't want to do that. So that's why there's a 1 plus. because we're going to earn a little interest. We're going to add a little interest to our account, not take it away. And then we're going to talk in a second about credit cards and how the plus is bad.
Yeah.
When we get to credit cards, we want to cry then. Because if they would do it the other way on credit cards, we'd be like, okay, I did owe $5,000 today. I only owe $4,000. Tomorrow I'll only owe, wouldn't that be neat? Okay.
Yeah, but
You guys don't know because you don't have credit card debt yet. You have no idea.
a credit card.
Oh, it's the most depressing thing in the world. Okay. Anyway, when you hear advertisements from a bank, the percentage or the rate that they are advertising is always an APY. It's an annual percentage. Okay. So that's how much money you would make over the full year. Kind of sort of depending on how often your money is compounded. Do you know what this word means?
Like how often you get interest.
Yeah. Do you guys know, like in my checking account that I have right now through UCCU, every month at the very end of the month, there's a little deposit into my account that's called dividends. Have you guys ever seen that on your account before? That's the microscopic interest that I'm earning on the money that I have sitting in the bank. And it's honestly the most depressing number in the world. They're like, here's your 9 cents for this month. I'm like, I just want to flip them off, but I don't. I try to keep my middle finger to myself, but it's fine. Okay, I'll take my 9 cents. So they're so gracious with it, you know? Anyway, so that means that my money must be compounded monthly because that's when I'm receiving that amount. Does that make sense? If your interest was compounded daily, you would see one of those little things every single day. What is the benefit to compounding daily versus compounding monthly? Do you really get more money? Oh, it's so tricky. It's so tricky.
Because you'll have more money in your account because they put more money in, so that interest that you got from them starts compounding.
So I used to have students all the time that would be like, yeah, but if it's 5% interest, if you're making 5% every day versus 5% at the end of the month, then obviously you're making more money. That's not exactly how it works. If it's 5% interest, if it's compounded monthly, then they take that 5%, divide it by 12, and that's how much interest you earn each month. If it's compounded daily, what do they do to that 5%? Divide it by 5% divided by 365. That's like giving 5 pizzas to 365 hungry football players. Okay, well, I guess we won't eat. That's fine. Yeah? So 5% divided by 365 days seems like, why even bother? Why even bother earning interest if you're going to earn such a small amount of interest? Well, if you take that tiny little bit and you deposit that extra ½ cent into your account every day, they don't really deposit half cents, but just so you know. Anyway, if you deposit just a tiny little bit every day, do you understand that the balance in that account is now growing? So then the next day when it goes to calculate that tiny little percent, there's actually more money, which makes the deposit bigger. More money, bigger deposit, more money, bigger deposit. So theoretically, you get more money. That's assuming you have enough money in your account for 5% divided by 365 to actually do something. Yeah, that makes sense? That's this piece right here. So the rate is going to get divided by how many times or how many times that rate has to be equally split. So how many times it's compounded is your N. And then you're going to raise that. So you multiply the money that you put into your account, the P, you multiply that by 1 plus the rate that you're earning, and you do it this many times. So however many times it's going to be compounded per year times the number of years. Do those little bits and bobs all make sense to you? Yeah, I promise if you work with this formula on your homework, it'll just kind of become a part of who you are. You say, do we really have to memorize it? You'll know it. By the time you're done with this assignment, if you really do the assignment, you'll know it. Okay? So we could say something like, how much will I have in my account if I am earning interest on $5,000 paid at an interest rate of 7%. So this would be what number would I put in here if it's 7%? 0.07. Watch your decimals. So 7% becomes 0.07. Compounded monthly, what would I put in the N? 12. And I would put it up here again. Yeah? How much money would I have after, let's say, 5 years? So I would put a 5 up there in the T. And then I just throw it in a calculator and voila, I know how much money I have. That sounds pretty easy. Okay. Then there's PERT. This guy. Why is PERT a thing? What did we say about E earlier? What is E? It's the exponential base that happens in nature. Okay? I have a question for you. When bunnies make babies, is it compounded daily, monthly, annually? So the growth in the bunny population, does it only happen on January 30th and February 28th? And is it compounded monthly? All of a sudden, all the bunnies have their babies on that one day? Why not?
That would be weird.
A little bit. Can you imagine if you could look at your calendar and be like, oh, here come the babies. Oh, there they are. So it's not compounded monthly. Is it compounded daily? So at midnight every day, that's when there's an increase in the bunny population? No, not exactly. So populations, like I use bunnies because it's uncomfortable if we talk about people's populations and all the details there. But with bunnies, they just do whatever they want, whenever they want, right? And the babies just magically appear whenever. Yeah? That is nature. That's the gist of the E, the base. It's things that happen in nature, so things that are continuously happening and changing. So that growth rate for a bunny population, if I use the base E, it's more accurate. It's things that are constantly changing and constantly happening. Well, if you were given the option between money compounding just once a year, December 31st, once a month, the last day of every month, once a week, once a day, or every split second of every single day, which one would you choose? Every split second of every single day. Because if your money is being compounded continuously, then that gives you the highest gain, right? You earn the most interest if they're always putting that extra money into your account before they compound it again. Does that make sense? That's what this is. So take out all this fluff up here, all the rate and the number of times and all that, and just replace it with E raised to the rate times time. Again, please be careful with your R. If it's 6%, what is R? 0.06, 0.06. Yes? Be careful with that. Okay, what's P again? It's called the principal. It's how much you start with. And A, it's the amount in your account with respect to time. So the amount in your account is equal to the principal amount, so the amount you put in, times E raised to the RT. Okay? Your calculator has this button on it. Do not use a decimal approximation for E. Use the actual E button. Okay? So you'll need, if you don't have one in your possession, you'll need a scientific calculator today. Good? That's your lesson. You did it. You made it through. Super proud of you. So you have time to work on your homework. I think, oh, hi, Landon. I think, let me see here. Actually, I should go back here.
Are you doing Zoom every day?
I don't know. I thought today, because I had so much stuff on the computer, I decided to go ahead and do it so I could just record it and then save it for notes, I guess, for the people that are gone or that need a review.